So next up, we have Jeremy Rand with Inside the BuGS Graphics Code. So I'm going to turn it over to Jeremy.
Thank you all for virtually attending my KansasFest 2021 presentation, which I've titled Inside BuGS Graphics Code, or How I Learned to Stop Worrying and Love Chasing the Beam. A little Kubrick reference there, of course. There are a couple of things from the 80s that are particularly important to me. First, the Apple IIGS. My first computer was an Apple II Plus clone that my dad and I built, but in the summer of '87 we got a GS with 512K of RAM, an RGB monitor, and a 3.5-inch disk drive. That computer got me through a computer engineering degree and was my primary computer until 1996 when I got a B-Box. Also in the 80s, I loved arcade games, and my favorite by far was Centipede. It was so fast and had great controls thanks to the trackball. So I thought, what would happen if I brought these two things together? So I created my first arcade game for the GS, which I called BuGS. You can see the icon that Fat Dog provided. I think it looks great on the GS, and I really appreciate his help with the icon and some of the sounds in the game. I worked on the code for BuGS from June 2020 until February 2021 when I released version 1.0, and it looks like this. Obviously, it draws heavily from Centipede. I'm using the same sprites, and just like in the original game, each level has a different color palette. It plays more or less like the arcade game with the same bugs moving across the screen in the same basic way. And like the arcade game, it runs at 60 frames per second. That is on a standard GS running at 2.8 megahertz. There are a few differences though. The original game has a screen made up of tiles, 30 tiles across and 30 down. Each tile is 8 by 8 pixels, so that would require 240 pixels of vertical resolution. The GS only has 200, so I opted to shrink the gameplay area down to 25 by 25 tiles. This actually makes the game feel faster and more frenetic because the bugs travel across the screen that much faster. Finally, in version 2 of BuGS, I introduced an online database of high scores. If your GS has an internet connection using an Ethernet 2 or something similar, then you can see the top 10 scores online and submit your own scores to the database. I'm here to talk about the graphics code in BuGS, and I can tell you that getting to 60 frames per second was pretty difficult. There were multiple times in the course of development when the game loop was too slow, and I was worried I would need to abandon trying to maintain that performance. The super high-res screen is 32K in size versus the 8K of the high-res screen on 8-bit Apple IIs. And unlike high-res, there's no page 2, so page flipping isn't possible. You can do something similar to page flipping using shadowing. I didn't use that technique, however. The CPU is faster than an 8-bit Apple II and 16 bits wide, which is really nice, but it's not that much faster given the extra size of video memory. It's just hard to push that many bytes when you've only got 41,666 cycles per frame if you're doing 60 frames per second. Worse, the super high-res screen is in the slow RAM on the GS, so there's a performance penalty for each write to video memory. So it makes it pretty tough. Thankfully, there's some help out there. First of all, GS Tech Note number 70 has lots of great ideas about how to do fast graphics, using the stack to write to video memory and keeping track of what needs to be redrawn to minimize the amount of drawing, things like that. There are great suggestions in there, and the Apple II community itself is extremely helpful. I had help from some of the best Apple II developers out there like John Brooks, Antoine Vinot, Dagan Brock, and others. I have a long list of people I acknowledge in my README file, and their help was invaluable. So all is not lost. And that's it, really. Well, just kidding, but in a way it kind of is. Those things got me 95% of the way there. Most of what I will talk about today are pretty standard approaches to fast graphics on the GS, with some bug-specific implementation ideas. There's only one optimization that might be unique in BuGS, and chances are someone already did something similar and I just don't know about it. More about that coming up. First, we need to talk about the way BuGS breaks the screen up into sections and then tiles inside of those sections. There are 3 sections. The left section, which has the score and the number of lives, things like that. The gameplay area in the middle, where all the action happens. And the right-hand side, where nothing really happens. The entire screen is also broken into a set of tiles. Each tile is 8 by 8 pixels wide and tall. There are 25 by 25 tiles in the gameplay area, the left-hand section, is 13 by 25 tiles, and the right-hand section is 2 by 25 tiles. Each tile has some information that it tracks. It knows what sprite to draw inside of itself. A tile can be blank, can have a mushroom in it, a letter or a number, etc. The bugs in the player are not in tiles. They're drawn on top of tiles. When that happens, though, the tiles they overlap with are marked as dirty. That means the tile needs to be redrawn on the next frame. A tile can also be marked dirty because its content has changed. Maybe a blank tile now has a mushroom in it, or maybe the tile has a number in it to display the score, and the score has changed. Tiles know the tile numbers of their immediate neighbors. This is important so the game can mark all of the dirty tiles when a large bug is drawn over top of a number of tiles. With that information, I can now describe the game loop at a high level. This is what the game does every 60th of a second. To start, we assume that a frame of the game is already visible on the screen, and we have already calculated where all the bugs are moving to for the next frame. The dirty tiles are all marked so the game knows what needs to be refreshed, and we're just waiting to draw the next frame. Once it's time to draw the next frame, all of the dirty gameplay tiles are redrawn. This erases all the visible bugs, the player, and the missile so they can be redrawn at their new locations. Once that's done, the bugs are drawn at their new locations. This marks a bunch of tiles dirty in the process. Then the dirty non-gameplay tiles are redrawn. It's important this happens after drawing the bugs, and we'll see why when we get to clipping. The player position is updated based on mouse movement and is drawn. The missile, if any, is updated and drawn. Then the game needs to calculate where all the bugs will be for the next frame. By the time this is done, it is ready to draw the next frame after this, so hopefully the 60th of a second has not expired. Here's a subset of the suggestions from tech note number 70. What is happening with the dirty tiles is it is basically managing a change list, which is one of the suggestions from tech note 70. Rather than redrawing the entire screen, which isn't possible on the GS, BuGS keeps track of the set of 8 by 8 tiles that need to be redrawn. So this idea from the tech note has been implemented through the use of dirty tiles. But what does it mean to map the stack onto video memory? First of all, the stack is a very efficient way to write data on the GS. 2 bytes can be pushed onto the stack in as little as 5 instructions, which is very good. There's a limitation of the 65816 processor, which presents us with a problem though. Memory is split into a series of 64K banks, and the stack can only be somewhere in bank 0. You cannot put the stack in an arbitrary bank. The video memory we need to write to is in bank E1 at hex address 2000. The GS has a feature called memory shadowing, and with shadowing on, a write to bank 1 in the video memory range will be shadowed to E1 where we actually need it. But the stack is still stuck in bank 0. The GS, however, needs to behave like an Apple IIe or IIc when running 8-bit software, and those machines commonly had 128K of memory, even though their processor could only access 64K at a time. These 8-bit machines accessed this extra memory through bank switching. They have a main bank of 64K, which is what is normally accessed, and an auxiliary bank. And the machines have soft switches, which direct memory reads or writes to the main or to the auxiliary bank. On the GS, the main bank is bank 0, and the auxiliary bank is bank 1. And in order to be able to run software which expects to read and write to the auxiliary bank through soft switches, those switches must also exist on the GS. Even though the processor is 16-bit and can access these banks directly, the software it is running may be 8-bit and may try to access auxiliary memory through soft switches. The GS brought these switches together into a state register at address C068, and using that we can direct reads and writes that normally go to bank 0 to instead be redirected to bank 1, which includes writes made to the stack. Every routine which draws a sprite in BuGS begins and ends with this assembly code. First, interrupts are disabled. If we were to handle an interrupt, the processor would push its state to the stack. Since the stack is going to be in video memory, we definitely do not want the video memory to be corrupted because some interrupt occurred, so we disable them. The next 2 instructions save the current stack pointer to a location called backup stack. And then the next 3 instructions cause writes to the stack in bank 0 to be redirected to bank 1. It clears the carry bit because sprites often need to do add operations and we don't want a carry to happen. And finally, the value in the Y register is moved to the accumulator and the stack pointer. When a sprite routine is called in BuGS, the caller always sets the Y register to the address where it wants the sprite to be drawn. So now we have the stack where we want it, like this. Then some sprite is actually drawn. When things are done, we unset those bits in the state register to undo redirecting our memory accesses to bank 1, restore the stack pointer, and re-enable interrupts. So that's the header and footer of every sprite routine. Now that we have the stack where we want it, we can draw a sprite, and that code looks something like this. This is the sprite code for drawing a blank tile. The first thing that happens is the X register is set to 0, and then X is pushed twice to the stack. This writes 4 bytes worth of zeros to the stack, and that puts those zeros into video memory. 4 bytes is 8 pixels, so that's 8 pixels wide of the first row in the tile. Remember from the sprite header that the accumulator has the original address where the sprite should be drawn. Next we add A0, which is 160 decimal, to the accumulator, and then set the stack register to this value. By adding 160, we drop down a line on the screen. Each line on the super high-res screen is 160 bytes wide. Then we push X twice again to turn the next 8 pixels black. The second row in the tile is now drawn. This happens 6 more times until all 8 rows in the tile have been set to zeros. The same kind of thing happens for more involved sprites like mushrooms and letters. So we've seen some more examples now of the suggestions from the tech note. We've seen mapping the stack onto video memory and using the stack to efficiently write to memory. We've seen unrolled loops. The sprite code could have been implemented as a loop over the 8 lines in the sprite, but loops introduce overhead for the compare and the jump. Instead, the code has no conditions, no jumps, just linear code. And the sprite code is pure instructions. It would be possible to write a generic sprite draw routine which takes some data and copies that data into memory. But like loops, a generic routine which can draw any sprite based on some external data is always less efficient compared to a routine which just draws a blank tile, or a routine which just draws a mushroom. We haven't seen the video counter yet, so that is next. This slide is drawing a frame in BuGS as the GS does, just at a slower pace. The frame is drawn from the top down by a beam that traces each scan line. Originally, BuGS waited for the vertical blanking interval before drawing the next frame. That interval starts when the previous frame is completely drawn. So when the last line of the screen is drawn by the beam, then BuGS would wake up and start drawing dirty tiles. But BuGS was unable to keep up with 60 frames per second if it waited for the vertical blanking interval. Once the beam has finished drawing the first 8 scan lines on the screen, however, BuGS could redraw any of the 25 tiles on the top row. Similarly, for the 16th scan line and the next row of tiles. That is the key optimization here. So here's the screen being drawn again slowly, and you can imagine that just as the beam gets past scan line 8, if the game changes anything on that top row in memory, those changes will not be visible on the screen until the next frame is drawn, not this frame. And really what we're trying to do here is increase the amount of time that the game can be writing to the video memory. On the GS, there's a vertical counter and a horizontal counter that gives you information about where the beam is. BuGS only cares about the vertical counter. Also, reading the counter is a bit tricky given how it appears in memory, and I'm not going to go into those details. Suffice it to say that it is possible to pull a couple bytes in memory and watch for a particular value and know that the beam is below scan line 8, or the beam is below scan line 16. And once we have this, the code can redraw each dirty tile in all the rows that have already been displayed by the beam. So what really happens is that the game is updating the state of the BuGS from the previous iteration of the game loop when the beam starts drawing the current frame. By the time the bug updates are done and the game is ready to start drawing the next frame, the beam is generally a quarter of the way down the screen already, displaying the previous frame. So right away the game can redraw the dirty tiles on the top 1/4 of the screen to prepare that next frame. By the time the beam gets to about the bottom quarter of the screen, the game generally is caught up with the beam. The top 3/4 of the screen has had all of its dirty tiles redrawn, and now the game is waiting for the beam and redrawing the remaining rows as the beam passes. Once the beam gets to the bottom of the screen, all the play area tiles that were dirty are redrawn and the rest of the game loop can execute. There's more loop unrolling here. It would be possible to have a loop over all the rows of tiles watching the beam, and then an inner loop over all the tiles in the row to redraw the dirty ones. Instead, this is all unrolled. There's code that waits for the beam to get past scan line 8, and then it checks each of the 25 tiles one at a time in that top row to see if they are dirty, and if so, redraws them. And then it does the same for scan line 16 and the next row of 25 tiles. all the way down the screen. So the entire thing is completely unrolled to make this as fast as possible and avoid unnecessary loops and loop condition checking. So now we've seen how BuGS uses the video counter to maximize the amount of time it has to draw the frame, and that covers the details about how tiles are drawn. But what about the bugs that are displayed over top of those tiles? In the gameplay area, a tile is either empty or has a mushroom inside it. The contents of these tiles are considered to be background, while the bugs are drawn on top of these tiles in the foreground. The bugs in the game overlap with one or more tiles, and the bug keeps track of which tiles it overlaps with. He needs to know this in order to know which tiles should be marked as dirty. Here we can see a scorpion which has been drawn, and it spans 3 different tiles. So when the scorpion is drawn, it marks these tiles as dirty. The key is that we need to be able to erase the scorpion where it is being drawn right now, because the next frame after this one, the scorpion will need to be moved. So the dirty tiles redraw themselves, which has the effect of erasing the scorpion. Then the scorpion is drawn at the new location, which causes it to animate across the screen. At some point, the scorpion is moved enough that it is no longer overlapping with one of the tiles, and instead it now overlaps with some other tile. So it has to update the set of tiles it dirties as it travels. The same kind of thing happens for the other bugs, the player, and the missile. They know where they are on the screen and know which tiles they dirty. They draw to the screen using the stack in a similar way as background tiles, but things are more tricky because they are drawing on top of the background. More on that later. One of the tricky things is that sometimes a bug like a scorpion or a spider is only partly visible on the right or left hand side of the play area. When this happens, we need to clip the bug so it doesn't end up drawing outside of the play area. What actually happens is that the bug does draw outside the play area. Here are the dirty tiles. 2 of the tiles are in the play area, but one on the right is a non-gameplay tile. We redraw play area tiles in order to erase the bug so it can be moved, but non-gameplay area tiles are erased right after the bugs are drawn. So when the scorpion is drawn, those 2 play area tiles and 1 non-play area tile are all marked dirty. But right after drawing the bugs, the non-game tile is redrawn, and this happens before the frame is shown to the user. By redrawing the non-game tile, we've clipped off the part of the bug which is outside of the play area. You can see that in the description of the game loop I've shown previously, redrawing the non-play area tiles is shown as happening after drawing the bugs here. So that is how clipping on the right and left side works. What about the top and bottom? There are bugs which are partially visible on the top. Both the flea and centipede enter the screen from the top, and that means those bugs are sometimes only partially on the screen and part of them is above the screen. There are no visible tiles above the screen, but what the game does is that it allocates a chunk of memory just before the video memory, enough to allow a non-visible tile worth of space. So when a bug is drawn partially off the top of the screen, the entire bug is drawn, but some of that happens in video memory or in memory outside of the video memory, so you just don't see it. No bugs enter the play area from the bottom, thankfully. That would make the game much harder, but a flea does exit the screen at the bottom. A flea drops from the top to the bottom. So the trick I use for clipping at the top isn't possible at the bottom. The memory after the pixel information is special and describes information about scan lines and color palettes. If the game drew a flea beyond visible pixels on the screen, it would corrupt that scan line information or the color palette, and that's not good. My solution here is to not do clipping at the bottom at all. When a flea reaches the last scan line, it just disappears. It doesn't ever go partially off screen when exiting at the bottom. I wonder if any of you noticed the shortcut. The flea is pretty fast, so I'm not sure that it is that noticeable. The sprite drawing we've seen so far was tile background drawing. In that code, we didn't care what was there. Whatever it was just overwritten with the pixels we want for the background. But when drawing a bug, a player, or missile in the foreground, this drawing happens on top of the background, and that means there can be pixels there that need to be preserved. If a scorpion is passing over a mushroom, the mushroom should still be visible around the body of the scorpion, for example. The problem is that the code is writing to 2 bytes at the same time, and that means it is changing 4 pixels. But what if the sprite only needs to change 2 of those 4 pixels? Then we need to preserve the 2 pixels that are not being changed and modify the 2 that are changing. In order to do something like this, the game needs to do a read of the video memory to get the pixels from the background. Then it needs to turn off the bits in the pixels that the sprite wants to change. If we do not do this, then some bits set in the background on those pixels could leak into the foreground, and the result might be an unexpected color. Then it modifies the pixels it wants to set, and finally writes that back out to video memory. All of that just to modify 4 pixels, and these sprites are much bigger than that. If the foreground sprite wants to set all 4 pixels in those 2 bytes, then it doesn't need to do the extra work. It can just write the values it wants. But this costly load, mask, modify, write sequence can happen a bunch. Here are a couple examples of bug sprites which help to demonstrate where we might have this problem. The body of these bugs is mostly solid, but often these bodies don't line up on a 2-byte boundary, and that means the edges may need to preserve background pixels. Worse, there's these spindly little legs on these bugs with lots of space for background pixels to leak through. Definitely a bunch of masking would be required. The AND instruction is what will be used to mask those pixels, but that takes 3 CPU cycles and consumes some of our limited budget of time when trying to hit 60 frames per second. So this is the bug-specific optimization I've mentioned previously. The main reason I can make this optimization is because in the original game there are only 4 colors on the screen at any one time. Black for the background, a body segment color, centipede eye color, and the player color. But on the GS, each pixel has 4 bits, so it can be one of 16 colors, which is more than is required in Centipede. So what I did in Bugs is I took the 4 bits of each pixel and split it into a pair of 2-bit values. 2 bits set a background color and 2 bits set a foreground color. This table shows the approach. The decimal and binary columns show the value of the pixel as it would be written into video memory. The foreground column has the upper 2 bits from the binary column and shows the foreground color that the number maps to, if any. The background column has the lower 2 bits from the binary column and shows the color associated with those 2 bits. Finally, the visible column shows the actual color that is programmed into the color palette for this value. What is really happening is that if the foreground color is non-zero, then the foreground color is what's visible, regardless of what is in the background color bits. But when the foreground color bits are 0, then the lower 2 bits, which is the background color, is what's visible. In a way, I'm artificially creating a foreground layer and a background layer in the super high-res screen by splitting the color space this way. Let's go a bit further into the example. In this example, we will imagine we have a pixel with a green color in the background and a foreground sprite wants to make this pixel red. Because the pixel is green in the background, we're currently here. In order to turn this green background color into red foreground color, we need to do an OR operation with 0100. That changes the value to 0111, which moves us to this state. So just by setting 1 bit in the upper 2 bits, we've overwritten that green background color, and instead the pixel is now red. No masking was required, assuming we know the foreground color bits were 0 to start. And it doesn't matter what the background color was that we had before. If it was black, then when we do the OR, we go to here. If it was red in the background before, then after the OR, we go here. If it was off-white before, after the OR operation, we're here. And as we saw, if it was green before, then after the OR, we are here. No matter what, we get a visible red pixel, regardless of what was in the background before. This only works, though, as I mentioned before, if we know the foreground bits are 0. When a tile sprite is drawn, it always sets those bits to 0. But if 2 bugs are drawn in the foreground on top of each other, then masking still might be required. Turns out spiders and scorpions never cross paths on the screen. A scorpion is always in the upper 2/3 of the screen and the spider's in the bottom third. So in the game loop, the scorpion is drawn first after the dirty tiles. It doesn't need to do any masking because there can't be anything in the foreground at this point. Then the spider is drawn. Again, the assumption is made that there cannot be anything overlapping with the spider and no masking is required because the only thing in the foreground at this point is a scorpion and they never cross. There's more to this optimization. The next bug that is drawn is centipede segments, and they definitely overlap with spiders and scorpions. So it would make sense that masking would be required. Worse, there are up to 12 centipede segments, so that can be a bunch of masking. But a centipede segment is almost entirely green, and green in the foreground is special. To set a pixel to green in the foreground, we do an OR with 1100. No matter what color existed in the background or foreground, once you do an OR with 1100, it will always be green. The key to understanding this is that when you do an OR 1100, the result is guaranteed to have 11 in the upper 2 bits. And if the upper 2 bits are 11, then that is green in the foreground, and that means it will be green on the screen. This saves lots of masking. So instead of load, mask, modify, write, most of the bug sprites are just load, modify, write when background colors need to be preserved. The Scorpion and Spider do no masking at all because they assume they're drawing on the background color only. Centipede segments do almost no masking because they're largely green, and green never requires any masking. The only bug which does any significant pixel masking is the Flea. But even the Flea has some green in its legs and gets away with skipping a bit of masking. So in summary, most of what I've described is pretty standard stuff and described in TechNote 70. Map the stack to video memory, unroll the loops, etc. But I also did something a bit weird with color to create an artificial background and foreground layer on the super high-res screen, which was only possible because of the very limited color palette required of the game I was trying to reproduce. Thank you very much for your attention. I hope you get a chance to try Bugs. You can find information about the game at that first URL, and if you want to see details about how the game was implemented, you can check out the source code on GitHub at the second URL. Thanks, and Apple II forever.
All right, thank you so much. Let's see, does anybody have any questions? Scroll back through. A lot of people are saying it's amazing. Thank you very much. Did you study the original code of the arcade game as it is 6502?
I didn't have the original source for the game. I did have a version for, it's an Atari, what is it? It's not the 2600, it's one of the later consoles. There's source code for that around. I did have that. I didn't really look at it much. For the most part, I was using MAME and just watching it, recording videos of it, and trying to figure out what was happening when. And I also found the other big reference I found was a booklet that you could buy in the 80s on how to be good at Centipede, and it had all the rules, like when do fleas appear, when do scorpions appear, when do they get faster, things like that. So.
Is the spider movement the same as the original game? It seems like it.
Ish. I would say the one of the big differences is, I think there's been some people who say that some things feel different, probably because the random number generator is different, is what it comes down to. Plus some of the, there might be different weighting on certain actions that I just don't know about. It's hard to know. It feels similar to me, but.
This is awesome. Any plans for Millipede?
Millipede. I don't. No plans at the moment. I think I got to take a break, a retro break for a little while. But yeah, I'll do something later. I don't know what. No plans.
Did you consider crunching the score and use that to expand the 25 by 25 play area to something closer to 30 by 30?
Crunching the score.
Yeah.
So the score is off on the left hand side. So on the real game, the score in the lives is along the top, and I specifically moved that aside to maximize the vertical resolution I had. So there's no savings there. The only thing I could do to try to get 30 by 30 is to shrink the sprites down to like 6 by 6 or something annoying.
Are there any hidden Easter eggs or cheats?
No, I don't think so.
Would you tell us if they were?
Yeah. Well, I worry that people are going to try to hack the online high scores. Please don't. I did try to make them safe, but you could try. There is a secret there. Well, why am I tempting you? I shouldn't be tempting you with this.
One of us. Yeah, everyone's, why are you chasing the beam instead of running in front of it? Obviously, your code is fast enough. Breaks are understandable. Challenge denied. The plot thickens. Okay. Any last minute questions? Last second questions? Any other ports planned?
You should all be watching Peter Hirschberg I believe I'm saying his name correctly. He has done a port of Asteroids for the GS that is very good. So check that out. And he's working on Adventure, 2600 Adventure. So he's the one to watch. I'm taking a break.
Oh no, you a well-deserved break, and that segues nicely into our coffee break at